Hello everyone. We'll continue our discussion of problems in this lecture also. So the first problem we are going to address here is with this physical setup, and you note that this problem was just like a cantilever beam as we'd been discussing previously, but we have now made this problem statically indeterminate, and it now becomes a different sort of problem because of the presence of this roller support here. Okay, this is very much a statically indeterminate problem. Okay, so had this roller not been present, it would have been just a simple cantilever under uniformly distributed load, and that would have been statically determinate. Okay, but now it is not so. Now in the previous lectures we had been concerned with the direct application of Castigliano's theorem of deflections. We were interested in finding out the deflections at certain points. We also used a certain trick using the fictitious force method to find out the deflection at a point, deflections as well as slopes at a point where directly point forces or couples may not be applied. But it was at the end of the day just finding out the deflections and slopes. But now we invert the question, and now we are interested for this particular problem in finding out the reaction force at this end, okay, or this end. So let's say that at this end, let's call this end A. Okay, so we ask the question that what is the reaction force at the end A? Okay, now please note that if we simply go by the method of statics as we had learned in our undergraduate days, this particular problem is not really tractable. Okay, I mean it is a statically indeterminate problem, so that's the indeterminacy associated with it. We can't find out the reaction force, we can't find out all the reaction forces associated with this problem. Now let's see if we can do this using energy methods. Okay, now there will be a certain danger associated with it, which I will discuss subsequently. But for now, let us try to see if we can find out the reaction force. Okay, and the trick, the overall understanding or conceptual trick behind it is that you note that suppose we were to think of the reaction force at this end like a point force, and then we try to think that what is the deflection associated with that force. Okay, now of course because of this physical setup we know for a fact that the deflection here is equal to 0. Okay, it has nowhere to go, so the deflection here is very much 0. So that is the key conceptual trick involved. Okay, we find out the reaction force at this end using Castigliano's theorem of deflection with the knowledge that the deflection is equal to 0. So previously we had found out the unknown deflection given a certain point force. Here we are finding out the unknown point force given a certain deflection, but for both the cases we are going to use the Castigliano's theorem on deflections. Okay, so with this overall understanding we proceed we just like before that, we take a cut section maybe somewhere here, and we consider the part of the beam which is to the right of this cut section. Maybe consider it a little bit below. Okay, and let me complete the free body diagram for this. I have the distribution of forces of the same intensity as before, as shown here. I now also have the reaction force, I also have the reaction force at this end. Okay, let's say we call this R for reaction force, and we'll also have the moment here and the shear force. Okay, so as before, almost algorithmically, we proceed by first writing the expression for the moment. So this sense is clockwise, and the contribution to the moment due to this reaction force calculated about an axis which goes through this end. If we consider that this is our x, let me just write that down properly. So we consider our x from this end. So this entire distance is x. So that will contribute Rx, but in a sense which is anti-clockwise. So this is minus Rx. Next, the contribution due to this distributed load will be Wx, that's the force effectively acting at a distance x by 2 from this end, and the sense of the moment due to that effective force will be in the same sense as this m, so which is why we have this plus here. This x by 2 is the effective moment arm for this Wx force. So this is equal to 0. So this m is equal to Rx minus Wx squared by 2. Now, if we consider the deflection at A, okay, the deflection at A, or if you want to write it in the, so maybe you can write it like deflection due to R in the direction of R. So that will be using Castigliano's theorem, 0 to L m by EI del m del R dx. Now please note that earlier when we had artificially introduced the fictitious force, we had evaluated this entire integral for the value of the fictitious force equal to 0. But now the knowledge that we have is that we don't have any knowledge about this right hand side, but we do have the knowledge about the left hand side, as we had mentioned earlier, that this dr, that is actually equal to 0. Okay, because this dr is the deflection at this end A. Okay, that is equal to 0. So we evaluate this integral. This is Rx minus Wx squared by 2 divided by EI, and del m del R just gives us x dx. Okay, so from this we have 0 is equal to well, this is Rx squared minus W x cubed by 2 divided by EI dx, and this is going to give us, so let me just go here. This 0 is equal to well, this EI is not going to contribute anything because I can just multiply throughout by EI. So this is just R cubed by 3 minus W x to the power 4 by 8. This entire thing under the limits 0 to L, and that of course is 0 equal to R L cubed by 3 minus W L to the power 4 by 8. So overall what I have for R is 3WL by 8. Okay, and you please note that this is indeed dimensionally correct, because W has the unit of Newton per meter, so W times L is actually having the unit of Newton, and this reaction force R has the unit of, must have the unit of Newton. Okay, now regarding the, so this is our answer, as we have been asked to find out reaction force at the end A. Now regarding the danger that I was alluding to earlier, you please note that this entire method, it works for statically determinate problems, okay, but it is not going to work for statically this method is going to work for statically indeterminate problems. It is not going to work for statically determinate problems. And you can take a quick look. So we'll discuss this after the next example, but let me just write it as a fair warning here. So maybe with the red sign and the skull symbol. Okay, so there's a very, very big danger. Okay, rather graphic warning here, but I hope this will help you to remember it always with this graphic warning, that do not use this method for statically determinate problems. Okay, all right, let's move on to the next problem, which I will not solve in as much detail, but it will give us a good understanding of another variety of problem that could occur. So the situation is like this. We again consider a beam, but this time this beam is constrained or attached to two walls at the two ends. So at both the ends it is fixed. Okay, sorry, that is very bad. Okay, that's a little better. Okay, so this beam is attached to both the walls, or clamped at both the walls, and we have a point force acting vertically downward like this. The entire length of the beam is L. Okay, so let me not clutter it. Okay, you understand the length L of the beam as it is in all the problems earlier, but more importantly, this distance here, this is A from the left end. Okay, and what we are asked here is to determine the reactions, meaning both the forces at the moments at the two ends. Okay, so again, you note that had this beam not been clamped to this wall, this would have been a simple cantilever beam, and that would have been very much a statically determinate problem. But now, due to the extra, rather unnecessary support of this wall, this is no longer a statically determinate problem. It is a statically indeterminate problem. All right. So how do we go about finding this thing? So what we'll do is we'll we'll try to find out the reactions, and that is the forces of the moments at this left end. Okay, so let's draw this. Sorry. Let's draw it like this. Okay, what I have done here is basically I've taken a cut section here. Okay, and this is M here. I'll also have a V. Maybe this can be drawn a little bit better. And note that at this end, it is this M naught and this R naught which we wish to find out. Okay, so this R naught and this M naught, they are not known. And of course, we have this externally applied load. So this is of magnitude P. Okay, so as before, we write down the expression for M. So this is so this M is this M, and that is in the anti-clockwise sense. So when we write down the entire moment balance, the contribution from this will be with a minus sign, minus M naught. And if we take the contribution from this R naught about an axis which passes through this end, it is going to give us a moment which is R naught times X, but again in the clockwise sense, which is opposite to this sense of this anti-clockwise sense of M. And finally, for this force P, again the moment about an axis which passes through this end will be P times X minus A, but you note that this thing is going to get activated only for X greater than A. Okay, so this is H into X minus A. So I must mention that we are calculating our X from this end. Okay. And what is the sense of this movement? So it comes with a plus sign. Let me just check. So this distance is X minus A, that is fine, and that is the moment arm. So so that also has the anti-clockwise sense, same as this M, and this entire thing is equal to 0. All right. Now I'm not going to go through with the detailed steps of this, but you note that unlike the previous problem where we were interested in finding just one unknown reaction force, here we do not know the R naught, we do not know the M naught as well. So in order to find out these two unknowns, we need two equations, and the clue here is that because this end is clamped, we know from physical considerations and our undergraduate studies that the deflection here is going to be 0. Not only that, the slope here is also going to be 0. Okay, so based on those two facts, we can use the Castigliano's theorem in inverse using both the Castigliano's theorem rather and the corollary to the Castigliano's theorem involving the slope to find out the two required equations which can be solved simultaneously to find out the unknowns m0 and r0. So let me just write down those the things that we need. So it's like this, that the deflection d due to this r0, this is going to be integration 0 to L m by ei del m del r0 dx, and you note that this thing is going to be 0 from physical consideration. Similarly, the theta m0, that is integration 0 to L m by ei del m del m0 dx, and again this is going to be 0 from physical considerations. So if you just substitute the expression for m here, so you'll get fairly long expressions here. You can do that. You can do the algebra on your own, solve them simultaneously, and find out the answers. So let me just write down the answers for you here. So for r0, you will obtain, after solving, you will obtain r0 is equal to p times L minus a square L plus twice a divided by L cube, and you note that this is indeed dimensionally correct. Okay, so this is having the unit of meter square, this is meter, so that's meter cube, and in the denominator also you have meter cube, so at least it is dimensionally correct. And for m0, we are going to have minus p L minus a square times a divided by L square, and again you note that this is indeed dimensionally correct because this is m square, in the denominator you have m square, and this m remains, so this is Newton meter, and that is the unit of m0. So at least again it is dimensionally correct. So that these are our answers. Now going back to that danger that we had mentioned in the previous problem, you please note that I mean this thing, that danger will be immediately evident here. Okay, so you see, suppose this beam were not clamped at this end. Okay, suppose this beam were not clamped at this end, and given a question like this that determine the reactions, that is both the forces and the moments, suppose we naively proceed exactly like this. Okay, suppose we take a cut section here, we consider this m, this unknown m0 and r0, and we proceed like this. So there is absolutely nothing which is stopping us from proceeding like this, even if this beam was not clamped at this end. Okay, so that is for the case of the simple cantilever problem. So because if we proceed like this, we'll end up with these answers again, because the algebra is going to be exactly the same, nothing changes. But you note that if for a simple cantilever problem you obtain these answers, then definitely these are going to be wrong, because you know that if you just apply statics, okay, as you have all learned in our first year mechanics, the reaction force at this end, it is simply P, and the moment, the magnitude of the moment is simply P times A. So these answers are definitely wrong for a simple cantilever problem. Okay, so and the simple cantilever problem, the whole issue here is that the simple cantilever problem, that is without the presence of this clamped end, that would be a statically determinate problem. So as we had mentioned earlier, we are not supposed to use this method for those kinds of statically determinate problems. Okay, all right. So with that, on that note, I will end this lecture. Thank you very much.